take some time to think about it, and then also you'll probably answer some of your own questions on Monday, and then we'll kind of hit that up again on Tuesday together, okay? So work with me on thermodynamics. Labs to the side. Be respectful if I'm giving you information. If not, you can go watch your own YouTube videos on your own. So in terms of the stuff we already talked about, what were some ways that you saw disorder in your lab, your hand warmer lab? What did it say about disorder? Or entropy? It was actually in the pre-lab section. I'm asking a lot here to remember. Okay, I mean, or just tell me, like, what happened in the lab that increased the disorder? What'd you take? Took one thing, which was what? A salt, and we added it to some water, and then we made what? Salt water. Okay, we made ions in water. Okay, so we took this nice condensed, like, crystalline structure, lattice structure, we put it in some liquid, and we made ions. These are ions. Okay, what happened to the disorder? It went up. Okay, the letter that symbolizes disorder is S. So the delta S, which I usually write at the end, right? So you have your reactants, your products, and you write delta H or delta blank. This is delta S. Delta S, assuming standard conditions apply, because we were at room temperature, is actually positive here. So this is a positive sign. That positive means the disorder increased. So entropy, which is what delta S stands for, entropy, not enthalpy, entropy, that refers to the measure of disorder. So always think in disorder, not order. So in that case, that actually occurred, did that occur with you going, okay, please dissolve, like did you do magic tricks on it, or did it just happen? Just happen. What's the word for just happen? Spontaneous, or thermodynamically favorable. That's the preferred term. But spontaneous is like what most people recognize. They're like, you know, just went on a whim and you went to the store and you bought 3 pairs of shoes. You did that spontaneously. You just did it. Okay, so I've done that before. And I just told my husband it was thermodynamics at work, and he didn't believe me. But thermodynamics is always going to be driving for certain reactions to occur. We have some reactions that just don't happen, right? If they don't happen, it's not because they just don't happen. There are 2 reasons for it. It's usually because the enthalpy doesn't satisfy the universe, or the entropy doesn't satisfy the universe. We're always satisfying the universe in terms of amount of energy that is being contained or being released. So if we're trying to satisfy the universe, we do have to talk about the 2 factors, the 2 driving forces of reactions, and those are going to come to what we kind of pulled together today to talk about Gibbs free energy. So the reactions that occurred in your lab, you actually had 2 types of enthalpy reactions, the endothermic ones and exothermic ones. Most of them were what in this case? Endo or exo? Most of them were exos. That is the data that's been collected over the centuries to see most reactions that occur are exothermic. There are very few that are endothermic that actually occur. Endothermic is not very favorable to the universe because that means energy is being put back into the system, and that's not always very stable. Most of the time, systems want to release their energy because they come kind of down to their lowest energy state, which makes them happy, which makes them stable. So not very many things will be endothermic. The reason they can be endothermic, that's even possible, is because the entropy has driven the reaction to occur. So we're going to talk about those 2 things together now. And I'll share where some things are in your reference sheet. I'm skipping some of the practice. Some of the practice I had first. So with this talk, we do have to talk about the 3 laws of thermodynamics. And so one of them is one you've already heard before. Energy of the universe, or energy of the system is equal to energy of the surroundings. It's just one's exo and one's endo. So basically energy is conserved. And energy is going to be multiple forms of energy: potential energy, kinetic energy, heat energy, chemical energy, nuclear energy. We can keep going, but there's a lot of different energy types you could consider. But what we deal with in chemistry is generally the measure of kinetic energy, the measurement of potential energy, and the measurement of work, which work energy is going to be based on volume changes in pressure. So it was like, last week for us. But overall, this has to be true because the energy of the entire universe has to be constant. Because there's no new energy coming into the universe, there's no energy exiting our universe. It's just changing form within our universe. So the word universe is kind of like, what are we really talking about? We don't really know. It's a lot of stuff together. So I'm moving forward here. You don't have to write down definitions necessarily, just the idea. Oops. So in terms of taking that energy into two different ideas, energy, for what we're going to talk about first, is positional energy, and it's kind of related to potential energy, but it's not only potential energy. It's going to be talking about their relationship of particles to each other. And so that's entropy for us. That's a measurement of disorder. So the second law of thermodynamics, the entropy of the universe increases, means more disorder will occur throughout the reaction, or throughout the process. It doesn't necessarily have to be a reaction. It could just be like a phase change, which is not a reaction, it's a process. So if the entropy of the universe increases, something has to be getting more disordered. So if something is getting disordered, it could just be based on the arrangement of the particles with each other. So solids which are all really closely compacted with each other, they can then undergo a phase change, which would go from solid to liquid, where they start to spread out some, to gases, where they start to spread out even more. Well, this condensed, packed area, we call that ordered. That's very ordered. That's in a lattice structure, which, where's my little lattice? It's in a nice, very regular pattern. Whereas liquids, nothing's really regular about it except for they're next to each other. And gases, they're totally everywhere. They're crazy. Their disorder is very high. So this process of increasing disorder naturally happens. When I say naturally happens, it means it happens without any intervention. You're not going, okay, ice, you need to melt here. You need to melt. It's naturally going to melt based on the conditions that it's exposed to. So we easily can go to disorder through phase changes. But if the two driving forces of reactions that force a reaction to occur are enthalpy and entropy, and I'm telling you right here that the universe favors what kind of entropy? Positive or negative? Positive, meaning increased disorder, right? So if it favors positive entropy, which is increased disorder, and I told you the other one for enthalpy was favored which type of reaction? Exo or endo? Exo, and that's what we see most of the time, which means that's very common because the universe is allowing this to happen, is exothermic. If this combination doesn't occur, one would think the reaction doesn't happen. But if ice, we're taking solid, and we're going to liquid to gas, what kind of phase, is this an endothermic process or an exothermic process for this phase change? This is endo, right? Because we're taking energy, we're putting it into the particles to allow them to overcome their IMFs and reform, form a new phase. So it can happen. If this process being endothermic, positive, and the same process, of course, the disorder is increasing. Delta S is is positive, increasing disorder. You're like, oh, but not both criteria are satisfied. There's something else at play here. That's one more factor that has to be considered to see if this reaction will be spontaneous, meaning it will happen without intervention, and it's temperature. Does ice melt at all temperatures? No. It has to be at a certain temperature for it to happen, which it happens to be what? Don't you say the F word. 0 degrees Celsius. Thank you. So it has to be at 0 degrees Celsius for this first process to occur. The other ones are going to be at different temperatures. So we have this interplay between three factors that will say a reaction will happen spontaneously, or thermodynamically favorable, or it won't happen. So the enthalpy one we've had a lot more exposure to. The entropy we're going to get a bit more into, and then we're talking about Gibbs free energy, which is the delta G, which you'll start to see here soon. So it does matter that the disorder of the system is increasing, but that's not the only criteria you look at. Can I go forward? Yeah, okay. So this is in the reading. I'm actually going to not go over this right now. This is in the reading you're going to see. I'll go back if I need to in a second. Third law of thermodynamics is that crystalline structures, despite the fact that they're a crystal, they're a solid, they still have inherent potential and kinetic energy. Yes? These particles are still vibrating because they are at 25 degrees Celsius in the room right now. So they have, since they're at 25 degrees Celsius, they have some kinetic energy that's making them vibrate. If they didn't like each other as much as they like each other, my hand could go straight through them. Because they're moving, and my hand particles are moving too. I could go straight through the desk, I could go straight through the floor, I could go straight through Chloe, but the particles like each other too much, more than I like my hand. Yeah. So a perfect crystalline solid is generally, so it's not just like one thing, it's any solid in its correct arrangement, lattice structure. Metals can be perfect crystalline solids. Solids, ionic compounds can be crystalline solids. Iodine is a non-metal. It can be literally anything, but it's just a crystal. But it's a regular lattice structure. It's a regular, like this one is a regular arrangement of others with relation to the other things in its crystal. Maybe if there's contaminants, yeah, like ores, like different ores, and like, you know, when you go to a mine, you'll pull diamonds out and rubies out, but there's be garnets and other things that are embedded, so that would be contamination, so that would be an inclusion. Geology, yeah, inclusion, but it wouldn't be a perfect crystal structure. So, the point of this, though, is that everything has a positive entropy. Everything has a little bit of disorder, because there is no perfect crystal structure at absolute zero. What is absolute zero?
0 degrees Kelvin.
0 degrees Kelvin, or negative 273 Celsius. We have not achieved this temperature. I mean, it's the 21st century, but we can't get things this cold. Okay? But at this point, if this is a theoretical point, if we can get this cold, all matter stops moving. Okay? At that point, if all matter stops moving, it has zero disorder. Got it? But that's not the case. We never ever achieve that. So we call this our baseline. If 0 is the bottom, every single gas, liquid, solid has more disorder than 0, meaning all S values are positive. Okay, question? It's related to the kinetic molecular theory. So temperature is related to kinetic energy. Kinetic energy is the energy of motion. If you have 0 Kelvin, you have 0 motion, which means you stop moving. But why 0 Kelvin? Someone has done some experiments that are like way old, and we have the standard that we compare to. Sorry, FYI, it's kind of off topic too. The perfect kilogram that we compare all of our masses to is getting ready to be renewed. We have a kilogram, like a mass of lead or something. It's in like a museum in England, and they're getting ready to renew it. They're getting ready to update what the kilogram truly is. They have a perfect sphere, and I just wrote about they're updating all the SI units to make sure that they're still legit, because gravity has changed a little bit over time, and our axis has changed a little over time. Yeah.
What happens if you have a gas?
Shh.
You have like a gas in a controlled setting, and then you change the temperature instantaneously to absolute zero. What happens to the gas?
We can't. We can't meet absolute zero. They would
make the gas just like.
They would probably make it stop. No, they would probably make it condense and come back down to solid form. They would probably do that, I think. I'll ask my friend who might know this, but this is not just theoretical. Okay, guys, so we're going to go to some calculations. Oh, yes, question.
So say that S values cannot be negative.
The true S value, and this is S of formation. I didn't say that. S, which is entropy of formation at standard temperature, cannot be below 0.
So then that's not entropy.
So entropy is a measurement of change from beginning to end. So that's a good point. So the measurement of change, which is is actually delta S formation final products minus delta S of formation of reactants. That change can be positive or negative because things can either get more ordered or less ordered, but the S value that describes the one thing cannot be below 0. And that's the point it took me about 3 years to figure out in AP chemistry when I was your age. Okay, so these are just some structures that show you that you can look at an arrangement. You can see the crystalline structure. It starts to disform a little bit and take on like more movement, which the particles start to rotate. So perfect crystalline structure will be perfectly aligned, no movement at all. As you increase the temperature, they start to move, so the kinetic energy increases, so the disorder goes up. Okay, and then particles through a solution process. These I like to show you particulate diagrams because you were expected to know how they represent what they're representing. So we have we have a salt, which has a regular pattern. We add it to water with little Mickey Mouse ears. What is the black thing up here? What element? Hydrogen. When people say H2O, they write H with 2 O's. Honors Chem, man. Okay, so make sure you do know that, and then you can see the arrangement has made some movement occur, and as they disperse throughout, the disorder goes up as well. Okay, so I think we've killed this, but let's go through one more time. Different ways that you can increase disorder. Different ways could be solid, liquid to gas, so going from phase change. You can increase disorder that way. You can increase disorder by making an aqueous solution. Raising the temperature on something, even if it's still a solid, you go from 1 degree Celsius to 10 degrees Celsius, it maybe hasn't melted, right? Maybe it hasn't met its melting point, but it still would increase disorder. Just simply increasing the temperature on something. And of course, this temperature dependency is really probably related to the phase changes, but it really could be anything because temperature is our third component to consider. So, what if we're looking at a reaction standpoint and we see the same state and the same state on both sides? So if you see solid and solid, what would you say would happen with the entropy? So you think, right? But then you have to count the particles and see if there's more solids or less solids on the product side to see if you made more stuff. Question? You good? Okay. So going forward, let's do that through gas examples then. So with a entropy of a reaction, you're trying to look at just the change in entropy. You do have to look at the states of matter, but if the states of matter are the same, you have to go to counting the particle or the number of moles of particles same. So in this example of decomposition of calcium carbonate, we go from solid to solid and gas. Well, that's just blatantly obvious. What happened to disorder? Delta S is positive because we went from a solid to not only a solid but a gas, right? So that as you produce that gas, the disorder is much higher. But down here, I have gas, gas, gas. How many gas moles do I have on the reactants? 3 moles of gas going to 2 moles of gas. What happened to the entropy? So delta S is negative because it went from 3 moles of gas to 2 moles of gas, meaning we've condensed our gases in some way or form simply by just making more complex compounds. We made from sulfur dioxide to sulfur trioxide. So I'll talk to you probably Monday or Tuesday about the complexity of the molecules in terms of their entropy, but we're just doing basics right now. Moving forward, give me a thumbs up. Counting particles. Okay, so does this equation look familiar? Not the S, but the general format. You get this on your final exam in terms of the reference sheet, which I don't have someplace on my desk over there. But you should know you can do the same exact thing, but the only thing that you see different is that this one has a delta, meaning the change in the products to the reactants is important, but these don't have deltas, right? These are not changes of entropies. These are, changes of entropies. These are the entropy of that product, the entropy of that reactant, and you're doing your subtraction there. Now you're still applying your moles, which is the coefficient from the BCE, but these values here and here, whatever they are, they're going to come from a table in the book. So like I said, you will probably utilize this up at some point in time for some of these values, which I'll show you. So let's unleash your reaction, your equation. Oh my goodness, where is this in the book? And it says it's a state function because nobody cares what happens in between, we just care about the beginning and the end. So, like Appendix 2 in your book, it has a table with the substance, the delta H formation, the delta G formation, the delta S formation. Okay? It has every chemical compound that we generally use in that do matter. The unit that I didn't tell you yet for this is disorder, right? But it's disorder that's related to energy because we're always talking about energy. The unit of S is joules per Kelvin. We have made the transition back to Kelvin. So thermochemistry, you do all temperatures in what? Celsius. But thermodynamics, you do all temperatures in Kelvin because of that third law of thermodynamics related to Kelvin. And gases have Kelvin, so you really got to keep your facts straight. Okay, so I have some example problems at the end, but we're going to talk about the comparison of delta H and delta S now together. So if something, and this is the term you should use, if something if a reaction is going to happen without intervention, it just happens because it satisfies the universe, it's called thermodynamically favorable. For me, you can abbreviate that as TDF, thermodynamically favorable. The old term that we used to use in AP chemistry was spontaneous, but everybody was like, do students actually know what spontaneous mean? And so they were basically saying that students could not thoroughly explain what spontaneous meant because you weren't thinking about the thermodynamics of the process. So they were like, we can't call it spontaneous anymore. We got to call it thermodynamically favorable. So you'll see in old worksheets and old books and old FRQs of spontaneous, but it means the same thing. Okay. So in a reaction, if it's going to occur spontaneously, it's going to happen without intervention. So it means you're not going to add, so no catalyst, no spark, no fire, no decomposition. Like, it's going to happen, hopefully, without an intervention. Sometimes you have to get a little bit of a boost to meet the activation energy, but we'll talk about that as it relates to this later. So the two signs that are the two variables that we would be talking about is that it has a positive entropy, means increasing in disorder, and a negative delta H, which means it's releasing energy. And so both of these factors play into the fact that the system overall is more stable at the end, supposedly. Even though it seems like that's kind of counterintuitive if the disorder is increasing. If the disorder is increasing, they're spread out more, so they have less, maybe less interaction with each other, which would cause a more stable process overall. Can I go forward? I will say that our next unit, next thing we're doing is kinetics, and that's the rate of reaction. So thermodynamics has absolutely nothing to do with how fast the thing occurs. It's just that it occurs. Like over time, carbon turns to diamond, right? Over how many years probably? Thousands of years. But it's spontaneous. It happens without intervention. It just doesn't happen very fast. So don't think that you can now say, oh, it's happening fast or slow. You don't know that much information about the process. You only know if it's going to happen or it's not going to happen based on the two factors. Yeah.
So like if it happens naturally, but like by itself, but like with other like outside factors like pressure or like
I would not say that's necessarily an outside.
as in like putting in a diamond, like that's not like that happens like by itself, but like the pressure and like
For the that's the only thing that makes it happen though.
okay, yeah.
So I would say without outside intervention, like you're manipulating the variables, it's like a constant variable. Constant pressure and constant temperature most likely. I'll have to look into to see though what factors truly are outside interventions and not though. Okay, so the two variables that we now talked about, delta H and delta S, they come together to describe delta G. So delta G is the energy to do work, which is called Gibbs free energy. You can imagine who named it. It was probably Gibbs. And this is the variable that you can say delta G is negative, delta G is positive, and that positivity or negativity will also describe that it is thermodynamically favorable or it's not. So read for a second, then we're going to talk. Yeah.
Gibbs free energy or Gibbs?
Gibbs. Please don't, I don't know, you can say Gibbs's. I've always heard people say Gibbs.
So we're going to get to is the name just going to be that something with like consciousness?
I'm not important. Not important. Not important. Not important. Not important. Please just call it delta G. Okay, then we don't have to deal with that. So if a process is negative in terms of its delta G, its Gibbs free energy, it means it's spontaneous. So if it's negative, that means probably along the line, maybe your delta H and your delta S agreed with the universe, and so delta H was likely what? Negative or positive? Negative meaning exothermic, and delta S was positive. Now, these are not the only two variables, like we said, that are involved. Temperature can play a role to create the spontaneous reaction or thermodynamically favorable reaction. It's a little hard to say that. So we're going to talk about how that relates in just a second. But if it's a negative delta G, it's absolutely going to happen without intervention. And there are two other situations where delta G is not less than 0. If it's greater than 0, it's non-spontaneous or non-thermodynamically favorable. And these are memorized values, okay? You got to memorize it. If it's positive, it's non. If it's negative, it is thermodynamically favorable. And we're going to have a whole, 2 months on equilibrium. But delta G is equal to 0 at equilibrium, meaning the forward nor the reverse reaction is more favorable than the other. So they're like equally favorable. Does that make sense with equilibrium? Because all of these, everything we've been doing so far has been a forward reaction. We haven't talked about reversible reactions where you take your products and move back to the reactants, but we will. So right now, you're just assuming everything's going forward. Reactants are going products. So there's two more terms that actually biology uses a little bit more often than we do, exergonic and endergonic. And those are terms that Baby exam now is trying to emphasize. So it's definitely related to their spontaneity. It's related to the transfer of energy. So if you want to take a picture of that or write down the term, and then you can do more with that later. It's a term you need to know and be able to just talk about. It's not necessarily like applicable outside of saying it's endergonic or it's exergonic. So exergonic, it makes sense because you see the energy is flowing out of the system, exiting, flow in a direction that lowers the free energy of the system. So if you lower the free energy of the system, it's kind of like the same thing as these potential energy diagrams, but instead of being potential energy on the axes, it's going to be Gibbs energy over the time of the reaction. So if the energy starts high and ends low, to me you're going, oh, that's exothermic, but exothermic is relating to what variable? Delta H, but we're talking about delta G. So it basically means the same thing, it's just a different term. But this way, we're not talking about just about heat, which is exothermic. We're talking about the energy, all of the energy, which is a combination of delta H and delta S. And then same story, different way. Endergonic, the reaction absorbs energy. So absorb means it goes into the reaction. So how would that curve look now? Like an endothermic curve, but then we would call it endergonic because it's referring to the free energy, not the thermosity. Endothermicity. It's not talking about the heat, it's talking about the combination of variables. Okay, I think we're good here. I say we're good. Moving on. I'm going to hit the phrasing. This is the curriculum, like straight up the curriculum of AP Chemistry. I'm going to talk about that after we do some questions. Actually, no. Read that and write down what you don't want to. Because I still have about 20 minutes, so I think we'll be okay. Read that and write down what you need to. Because the phrasing is very important. Say again? Say again? Yes. So you see, they think you're stupid, but you're not. You got that? Okay. So we're going to talk about what this means when we hit equilibrium, but we'll kind of embed that throughout. Okay. So do you see this equation? Does it look very similar to all the other ones? Yes. They're so easy if you remember products minus reactants, except for what we did yesterday, which was, what did we do yesterday? But what did we do it for? Bond breaking and bond forming. So the bond dissociation energy one is the only one that you reactants minus products. Everything else, delta G, delta H, delta S, yeah, those are all products minus reactants. So again, you see the delta symbol here? That's because Gibbs free energy is a state function for each of the inherent energies embedded within these compounds. And again, these N values are what? Moles according to the balanced chemical equation. And where do you find these lovely pieces of information? Textbook. And that's going to be established at standard temperature and pressure, which what is standard? I'm sorry, standard conditions. Standard conditions. What standard conditions? 25 degrees C, which is, but which is what? 298 Kelvin. Okay, so remember when you're doing thermodynamics, you have to convert to Kelvin. Because now you see where temperature plays a role. Right here. This is the big mama equation you need to write down. That's what we're going to practice with right now. We're going to predict spontaneity or the thermodynamic nature of these things. It's called the Gibbs, no apostrophe S. It could be either one. Gibbs-Holtzman equation. Are you guys okay? Is this a lot of information or is this okay? Not too much? No, I'm sorry. It's not that I don't care, but I do care because I want to make sure that you have some time to process this by Monday. It's about processing. Okay, so now we're going to take these opposing forces, entropy and enthalpy, put them together, and talk about if they agree with each other to make the universe happy, make the universe satisfied, then Gibbs is automatically going to be what sign? Say again? Negative. But if they both disagree with the universe, meaning enthalpy is positive and entropy is negative, what will the Gibbs free energy always be? Positive, because it's like, it's never going to happen, people. It's not going to be spontaneous. No matter what temperature you put it at, it will never be spontaneous. But then you have those ones that are like, oh, well, one agrees and the other doesn't, but you can force it to be spontaneous or thermodynamically favorable if the temperature is just right. Okay, so we're going to solve for those. Yeah. And ordered. Endothermic and ordered. Oh, I have one for you. Hold on. Sometimes when supersaturated solutions, which have all their ions dispersed throughout the solution, sometimes when they precipitate, because it's supersaturated, if you disturb it, immediately it crystallizes. Sometimes that takes energy in. It would feel cold to the touch. Yeah? Okay. So here we go. This is I think the chart that makes the most sense between all of these. Do not memorize the chart, memorize the relationship. So let's talk about how each of these occur and why the temperatures will be high or low to force these reactions to occur. So we kind of already did this one. This is exothermic reactions, positive meaning more disordered. And which other one did we just talk about? Second one. So those will be, I say spontaneous at all temperatures. I really should change all my vocabulary to be thermodynamically favorable. Just saying, just so you don't think spontaneous is the term. But those two we have talked about because those two either satisfy 100% or not 0% of the universe's needs. These are different. So let's talk about mathematically how do you wrap your head around this. Why does a high temperature have to occur if you have an endothermic reaction and an ordered or getting towards order? Disorder. This is disorder, and getting towards disorder system. So apply that in your delta G is equal to delta H minus 2 delta S. Yeah. So talk to me about how that number, the math works out.
So if the H is high, S is high. The higher S, so like the higher disorder, the higher to make it more thermodynamically favorable,
Okay.
you need to have a higher temperature
than the delta H, right?
Yeah. So the delta H would be a set number, and the delta S would be a set number. So you need high T to ensure that delta S times the T is bigger than the delta H.
So that when you subtract them, it's
Positive.
negative, right? Sorry, negative, yeah. So the delta G has to be negative for it to be thermodynamically favorable. So how do you make it negative? You need to figure it out by the math. If you have T and you have a positive number here, positive minus positive, well, that could be negative or it could be positive. So how do you force it to be negative? Got a really high T here to make it a high number you're subtracting. So separately, so we got that one. And then separately, if I have, we want it to be negative, but we have an exothermic reaction, which is negative, right? Minus toss, so T delta S, which is in this case getting what? So what's happening to the order? Getting more ordered, which is bad. We don't want to be more ordered. How do we make this a negative overall? A negative minus a negative is actually negative plus something, right? But we don't want that to be too big, right? We can't have this value back here being bigger than this value. So we have to have a small t at low temperature for it to remain negative. Mathematically sane? You good? Okay, just making sure you can see that. And let's do an example. Oh, dang it. Hold on. Where are my examples at? Let me scooch this way. Okay. Write down your, this kind of problem-solving process first, because you will probably do this about 3 or 4 times on homework, and we're going to actually put an example with this. And I do want to make sure that you're understanding that these units are different. They're not the same. Delta G is usually established to be kilojoules per mole. Yeah, per mole. And then delta H, we've seen is what? Kilojoules per mole generally. And delta S, we just saw to be, say again, joules per Kelvin. Okay, so if you don't write your units, you're going to shoot yourself in the foot about 5 times, and you won't be able to walk. Okay, you got to be able to walk until next Thursday, which is our test. So units are important because these two will be fine, but then when you start to plug in your Kelvin here, Kelvin times joules over Kelvin, Kelvin will cancel, right? Well, then you're doing kilojoules minus joules. Well, that's not going to work. You got to pick your favorite. I usually go with kilojoules and just bounce this decimal back 3 spaces and call it a day. Call this kilojoules, but you need to convert first. You got me? Got me? And whenever you solve, so to make something spontaneous, your delta G needs to be what again? Negative, right? If it's 0, it's at equilibrium. It's got to be less than 0. So how do you display that here? You say, so I'm using inequality. Do I want to put it like this or like this? This, right? So delta G needs to be less than this, right? Delta G needs to be, oh, hold on, I'm going to put it down here. Delta G, which if I say it's equal to 0, that's the equilibrium. How do I write the inequality here to make it seem as if whatever delta G is equal to is less than 0? Like this, right? Okay, it's better if I put it right here. 0 is greater than this stuff. Yeah? Yeah? Okay, which is equal to this. You okay with that? Math? I'm just making sure. Sometimes that's rough. So then when you come down here and you manipulate your variables, you got your, how do I get this like this? Tell me math here. How do you from here to here? Wait, hold on. What do I do first? Add delta S to the other side. You can't divide until you get the subtraction out of the way. So add cos. So then you get T delta S is equal to delta H, and then what do? Divide by delta S on both sides. Okay, so then you get T is equal to delta H over delta S. So just make sure you can plug that in. So, but this inequality still stays. It's like this, right? And so what you're saying is that this is spontaneous at all temperatures below this temperature. Because it should be related to the fact that you've got to be lower than the 0 mark there. Okay, so all temperatures, whatever this is, all temperatures below that, it's going to be spontaneous. Does that make sense? Okay, let's actually do that now. Here's your decomposition. Plug your numbers in. Solve. We're going to solve problems together. But I at least want to get you go back to that video. And you guys will be reading more on this, but I want to get you a taste of it so that it makes sense more later too. Okay, it's funny. This is a note I gotta tell you, don't write this down. I was flicking through my notes, making sure I told you everything I need to today. Okay. So what are you guys doing up here? Tell me your setup. Okay, you write down your givens. Got you. Delta H is positive 90.8 kilojoules. Okay, what else?
For here, S.
Perfect, so let's convert that to kilojoules. That's easy enough. What are you going to do? 0.108. So that's 0.108 kilojoules per Kelvin. And you're just deciding on the temperature to make it spontaneous. So I'll explain this little part right here in just a second. I just didn't want to forget to tell you guys that before you had to go. All right, so first off is think about what we just talked about in that chart. This is endothermic. This is increasing or decreasing disorder. It's either positive or negative. It's not about the size of the number. Don't think it's lower than 0 or greater than 0. It's positive, so it's increasing disorder. Okay, so think about that. And I'm just going to see if you guys can do this. If delta G has to be negative, and you do delta G minus TOS, okay, okay, and this is positive, and this is positive. Temperature has to be lower high to make it negative. Okay, so this has to be a higher positive number than this one is to make it negative. So we already know temperature is going to be high. So think about that and just kind of put that as a note to yourself. So then mathematically, what are you doing over here? So you're doing delta G. So
For the T, delta S.
So I want to see the zero and inequality thing here.
0 is greater than
So 0 is greater than. I'm actually going to go ahead and solve for T first versus plug numbers in. Plugging numbers in early is like sometimes a little hard because then you might make a mistake. So pull everything over here and divide, and what do you get? T is greater than delta H over delta S. I know we just did that, but you should be able to reproduce that by yourself too. Then you plug in, what do you get? I'm sorry, I'm a little slow. 0.108 kilojoules per Kelvin. Kelvin comes back to the top right when you have it on the denominator. What is that value? 841 Kelvin. So temperature must be greater. Temperature must be greater than 841 Kelvin to be spontaneous. Temperature must be greater, so it must be high. Yeah? So temperature must be greater than 841 Kelvin to be spontaneous, or to be thermodynamically favorable. Okay. Last thing I told you what I just wrote down. So you guys know that those delta H values that we've been looking at, the three elements are 0 because they inherently don't have an enthalpy change within themselves on the formation of that. So delta G is the same way. If you ever have a free element and you don't have the delta G value for it, it's because it's 0. They don't tell you that. So that's a memorized fact. You should know that. So the delta G and delta H are very similar. Delta or S, maybe not delta S, but S itself will never have a 0 because we're never going to have 0 Kelvin with a perfect crystal. So those will always be positive values. Those will always be high. The change in itself can be negative because it's a change over a course of reaction. But just if they never give you the delta F, if they never give you the S, a formation for a particular something, do not assume it's 0. You need to probably look it up in a book. Yeah.
So if it is perfect crystal at absolute 0,
That's the only time it's 0, but we'll never have that. Never have that. Okay. So I'll finish this up, the rest of this on Tuesday. But I just want to make sure that you will be giving me your lab notebooks. If you need to by the end of the day, that's fine. I won't grade them during third period, trust me. But I'm going to have you guys share out still, and I know that we're not going to have to do it, but I'll try to get some time on maybe Wednesday next week. If I can, because I think that talking about it for your test is going to help you with your explanation. Okay? So you probably need to get with your crew and finish wrapping up a couple things, maybe make some plans, and I'll still working on logs again. Is that? Yes. I'm taking the two problem sets I asked for, they should be in the box. Enthalpy problem set, practical problem set, lab visits. The only grade 3 things I'm getting today is your NSMI thing might be really good to study from, but I need to look at those eventually. On your last grade. I'm not taking it. I know you're working your labs. I just want to make sure you do know where your homework is. Eyes. Really quickly, eyes over here. So it says on the board over here, more enthalpy problem set, because you want to be good at enthalpy. So the second page, it says more enthalpy problem set 1 through 9. 9 questions. And then only the textbook, it says entropy problem set from Zumwalt textbook chapter 15. It gives you like a little printout of the textbook, and it's only those questions. And I might even split. I actually think I've dropped down some of those. I need to look on my website because my slides sometimes go back to my website. So it's going to be on this slide or on this page. You'll find the packet. So just don't forget the packet. So I don't think I have this stuff on. Okay. And it's in your packet. And it's that plus the more enthalpy.
So this is on the G4 test reactions.
Okay, gases, yeah.
Some of them, like when I put,
It depends.